This is a quick demonstration of how to set up and visualize quad maps in Vizard. At a basic level, quad maps are meshes composed of quadrilaterals that can be attached to a body, whether that be a planet or a spacecraft. So there is a scenario titled Scenario Quad Maps that details some of their implementation, which we'll take a quick look at. This is a pretty basic scenario with a single satellite in a an eccentric MEO orbit. We set up quad maps down here. Now there are a couple different ways to do so with some tooling we've implemented. So within Viz support, there's an add quad map function. You give a unique integer ID for each quad map, the parent body, whether that be Earth or a spacecraft name, the list of vertices for the mesh. So the way this is generated is giving the XYZ position of the first corner in one quadrilateral, then the second, third, and fourth corner going around in a loop, and then appending all quadrilaterals back to back in a mesh. So you essentially have 12 floats per quadrilateral within the mesh. Now generating these meshes can be a little tricky, so there are some pretty basic helper functions within this quad map support file that is imported from Viz support, so we can access them within the scenario. These may be expanded upon at some point if there's specific desire for specific meshes. Then you can give a color and label for each quad. So we've got a couple defined as rectangular meshes. Now these are rectangular in polar space, so defined with latitude, longitude bounds. This one is the Arctic region, so north of the Arctic Circle. And then the last input to this compute rect mesh is the maximum angular width. So since we're wrapping a mesh over a convex surface, I'm specifying that each individual rectangle within the mesh cannot have a latitude or longitude delta of larger than 8 degrees. So this just helps, wrap that surface onto the convex, or wrap the mesh onto the convex surface. We set up Colorado as well, which is defined purely by latitude longitude bounds with a maximum angular width of 5 degrees. And then on the satellite, I've highlighted a solar cell on one of the solar arrays. So these are the body fixed coordinates of the corners of that solar cell. And then lastly, we've built two other functions. So one computes the camera field of view box. If you have a camera that's looking at a celestial body, you can project the field of view rays from the corners of the field of view, find the intersection point of the field of view with the reference ellipsoid, and then so this compute on the right here, this compute cam fav box just gets the corners of the field of view intersection points, and then we can subdivide, interpolating into an n by n grid that again helps wrap over the convex surface. So this is set up in the scenario here where we're taking an image every 20 minutes. So we compute the corners and then interpolate to make a 3 by 3 grid by passing in this field of view subdivisions. And then halfway through, we change a couple colors and labels, which I can give a quick demo of here. So we load up the saved binary file. Let's zoom in on the two rectangular regions. So we have Colorado, which is set up with its latitude, longitude, and labeled. And then the Arctic region, which is from 66.5 degrees north up to the North Pole. Around the halfway mark, so we're just about there now, we'll see Colorado changes color and the label changes. So you can look at the example for how to, the example code for how to do this. And then the Arctic region, I turned on its is hidden flag. So it still exists, but is currently hidden. We also have a camera set up. So you can see this field of view in the top left. When it takes an image, it's projecting its field of view onto Earth's surface. And since this is an eccentric orbit, you can see that that field of view grows as it gets further away, as expected. So this just kind of shows what would be imaged if you were to take an image every 10 minutes. And then if we look closer at the satellite itself, we also have in its body fixed frame, this orange solar cell here is highlighted on one of the solar arrays. So this is just a quick demo for how to set up some of these things, and yeah, hopefully this is helpful. Take a look at this scenario and documentation for more help. Thank you.